Everyone doing? Good. Thumbs up, I love it. Okay, good. Good vibes. Okay, great. Sorry, the slides, we're just uploading the slides. There was a technical issue, but the slides should be uploaded in like a few minutes if you want to follow along. And also, we've noticed that the dates on the website are completely disordered. Thank you for anyone who pointed out. We're going to update the dates today. They're basically just going to be in order up until the, yeah.
Are there like two different date schedules? Like one is like not?
No, I think it's just the dates are, like, I shuffled around some of the lectures. I changed the order, but then I forgot to update the dates. That's basically what happened. But we'll update them today, and then everything should be correct. Cool. Yeah. Any other administrative or website bug problems that people have noticed? Yeah, please just post them on Piazza. Okay, cool. I think then we can get started. Today is going to be an interesting lecture again. Just like last lecture was already a lot of fun. I hope you agree. Today is going to also be very fun. Today we'll talk more about scene representations. But first, I saw this on Twitter the other day. So this is the International Conference on 3D Vision, which is like the biggest conference on 3D computer vision. I told you this is a meme in the graphics community. This was posted on Twitter like literally like 3 days ago. So select all squares with the correct 3D coordinate system. If there are none, click skip. So I hope that you can figure it out. So okay, I'm going to ask someone to. Actually, it's impossible to judge whether this is correct. PyTorch 3D. Okay, well, I wanted to try to do it, but like actually it's not. It's actually kind of hard to judge which what. Okay, but maybe like at least the z-axis. Is this correct for OpenCV or no? Yes, good, nice. So which direction does the x-axis point in the OpenCV coordinate system? Well, I know I gave it away. Yeah, exactly. It's pointing right. And where is the y-axis pointing in the OpenCV coordinate system? No. Exactly. Okay, cool. Anyways, so this is an ongoing meme. I'm sure if you stay in this field, you'll see it again and again. Okay, so last time, brief refresh. The topic that we landed on last time was unsupervised depth prediction, unsupervised monocular depth prediction. And the task was basically as follows. I give you a data set of videos where each video is of a static 3D scene ideally, so nothing in the 3D scene is moving. And the question is, given just this data set of videos, can we train a model that learns to predict the depth given a single image? And the answer is yes. Yes, we can. And the question was how. Just as a brief refresher, how did that end up working? It ended up looking kind of like this. We take the frames of the video. We have a depth prediction neural network, just like a monocular depth prediction network that takes an image as input, predicts the depth. Then we also have a network that takes two frames of the video as input and predicts the pose. And then how did we use that to train our monocular depth estimator? We used that by basically warping the frames onto each other. So we basically took the depth and the pose, and then we applied this warping, which basically means you unproject, and then you render the point cloud from a different angle, right? And that allowed us to supervise this only by basically a reconstruction loss. We talked a little bit about how it works. I showed you how that looks like. That was 2017, so like almost, I guess, almost 8 years ago. This has obviously improved much. So this was from 2021. So it's starting to look quite good. And then we didn't get to two more details that I wanted to talk about, and we're going to talk about them today at the beginning of the lecture. So there are a few assumptions that are baked into this model. The first assumption is that we are assuming that the scenes are static. Why is that? The way we are generating the frames is really only by transforming the camera. So we're not changing anything in the image. So if something in the scene moved while from frame to frame, we will not be able to correctly generate these pixels. Does that make intuitive sense? Okay. And so what that leads to is if you just train this model and you just ignore that fact, you ignore that it assumes static scenes, then what happens is that objects that actually move often get placed at infinity. So here are models that are trained with this warping loss, but without accounting for dynamic parts of the scene. And what you can see is happening is basically that this car is just a black splat because it's just placed at infinity, because the model doesn't know what to do with it, so it just places it at infinity. Okay, so I wanted to bring up two ways in which people have dealt with this. So this is a paper called Digging into Self-Supervised Monocular Depth Estimation. They propose a model called MonoDepth v2. And MonoDepth v2, I think, is a paper that many people still get back to for this general framework of self-supervised monocular depth estimation, in the sense that this is still kind of like a paper that if you would ask me to get into this topic, I would send you that paper and ask you to read it, just because they do a very good job at synthesizing all of the different parts of all of these little hacks and tricks that allow you to deal with these different limitations. And they propose a specific way of dealing with this limitation. And let me show you what that looks like. So the problem with things that are moving, one problem is that you get occlusions and disocclusions, right? So for instance, if you take your finger and you move your head from A to B, then you can explain almost all the pixels in this camera pose with the pixels that you observe from this camera pose, except for a few of them. And the pixels you can't explain are the ones that get disoccluded from behind the finger. So there are pixels, there are parts of the 3D scene that you can see from this angle, but not from this angle. And of course, these pixels you will not be able to generate just by warping pixels from this frame onto the next frame. Does that make sense? Okay, so if you try to just put a loss on top of these pixels, then weird stuff will happen, right? The neural network will try to generate these pixels in some way, but there is no correct way of generating them because it just hasn't seen them. So the neural network will, for instance, try to generate weird camera poses, or it will make the depth wrong, or it'll do some crazy stuff just to minimize the loss. And so these guys here had a good idea of how to deal with this. And the idea is basically as follows. And this is something that people also use in optical flow, which we're going to talk about later. This is actually a figure from the paper. I didn't make this figure. It's kind of a cute, cartoony figure. So what you're going to do is this is frame t. This is image at time t. And then this is the image at t+1. And this is the image at t-1. And now let's consider for a moment how this series of 3 frames can help us to solve this problem. There's this little fact. When you move the camera, and you look at the first frame and you look at the last frame, then almost every pixel in the intermediate frame you can explain by either frames that you take from the next frame or from the previous frame. And why is that? Let's look at the example of this tree, right? So here, if you go from t to t+1, there's these pixels here on the house that you didn't observe in this frame previously, right? So these pixels got disoccluded, so you can't explain them by pixels that you saw here. Sorry, that was actually the wrong example. We should go from here to here. So right here, you have this top left corner of the door, which you didn't observe in this frame t-1. So if you tried to render this frame here using the pixels from this frame, you would run into a problem. But if the camera is moving like that, of course, afterwards, you will have a frame that does observe these pixels. So you could think about taking these pixels from this frame instead. So what this paper proposed to do basically is to say, okay, we're going to generate the frame at time step t, but we're going to generate it by taking some pixels from frame t+1 and some pixels from t-1. And together, we should be able to explain almost all pixels that are generated by disoccluding parts of the scene. And then the only question is, how do you actually account for that in the loss function? And the way they account for this in the loss function is actually very simple, and it's kind of surprising. what they basically say is they do the thing that we discussed in the last lecture. So they predict the pose between IT and IT minus 1, and they predict the pose between IT and IT plus 1. So they get the poses for both of them. And now they just warp both of these frames onto the frame IT. So they basically take this frame, and using the pose and the depth, they warp it onto that one. And then they take this frame, and using the pose and the depth, they warp it onto that one. And now they just say, for every pixel, we're going to use the image that gives us the lowest loss. So we take the minimum of the losses across these two images. And if you think about the example that you have here, and this is exactly what they're showing here, right? What you would get is that when you try to use this image to generate these pixels, you will get a high error because you're going to try to warp those pixels there. It's not going to work. But if you use those pixels, you're going to get a low error. So you would automatically pick the correct frame to explain the pixels at IT. Does that make sense? Yes?
So this is sort of making the assumption that in the previous frame it might be occluded, but in the next frame it will be occluded, or vice versa.
That's right.
So if both those conditions fail at both frames, it's occluded. I guess maybe that's not a reasonable assumption.
No,
maybe
yeah.
It's a reasonable assumption.
No, it's a good question. So the question is, like, what happens if the thing is occluded in both frames? And let's try to think about when that could happen. So it would happen, for instance, if you had something like that. So like where something is moving and moving back. Then if you look at the intermediate frame, like my face, from your angle, my face is not occluded. But like from both of the previous and the next frame, the face would be occluded. And then you would indeed, then it's bad luck. But as you say, in reality, that doesn't happen all that often. Because in reality, like, the motion usually is smooth. So like, for instance, like a car, if you think about a car moving on the street, right? The car will be moving, and it's going to just continue moving in that direction. So if you take the next frame, the car will have moved a little bit further, and in the previous frame, it will be a little bit closer. So usually this assumption is reasonable. Any other questions? Great. So, and in fact, as I mentioned, this is actually this is a fairly general idea, actually. This is a fairly elegant way of dealing with occlusions in a way, to just like look at like consecutive frames. Okay, so this was idea number 1. And here actually you can see what that looks like. So here we have a frame. This is basically the frame T, and this is the frame T minus 1, and this is the frame T plus 1. And then the colors in this image basically tell you whether the pixel was generated by the next frame or by the previous frame. And what you can tell here, there is a region which is blue, I guess, blue, yeah, purple, right? The purple region here that you see, the purple region all comes from this frame, which is the purple frame. And you can see that this is exactly the region. This is exactly the region where the car goes from occluding the background to disoccluding the background. So you can only explain that with the. So I guess in this case, the camera moved to the left, which is a little bit confusing because you would usually expect the car to go forward. But actually, what happens here is that the camera moved from you're looking at the car like this, and then the camera moved to the right like that. Sorry, right. Look, the camera moved to the left, right? So like the car was close, and then the camera moves to the left, and the car goes from here to there to there. So it's like increasingly occluding the background, right? And then if you look at which pixels the model uses to explain the thing, it's using the pixels from the previous frame to explain the pixels that were disoccluded by the car, which makes sense. Does that kind of make sense? Like just as a visualization, yeah. Cool. And then actually this is the color frame is actually a little bit hard to see, but you can see here. So this is a figure from the paper. What you can see here is that this car that previously was just a black dot, which the model didn't know what to do with, the car now is approximately put at the correct depth. Okay, actually, this is a confusing thing. Skip that. Okay, then another thing that I wanted to discuss is that there's another little problem here, and this is also something that comes again and again. I'm going to draw something on the whiteboard, and I'm going to ask you a little bit of a tricky question. So, okay.
So imagine we had a 2D image, and in the 2D image, we would have a ball that is resting on a surface, right? And now I'm going to tell you the following. This image is generated via a little rendering process. And the rendering process only has one parameter, which is the position of this ball. So the position of this ball on the x-axis. So right here, maybe this is x equals 0. X equals 0. And right here, the position, let's say, was x equals 1. Does that make sense? So the ball is at x equals 0, gives this image. The ball is at x equal 1, gives you this image, right? Now imagine that the pixel values of this image would be differentiable with respect to this variable. What I mean by that is, like, if you wiggled this ball, like if I asked you, okay, how could I explain this? I'm looking for a way to explain this without giving away the problem. Actually, I don't know if you need to know this, actually. Like, let me just ask you this is actually unnecessary to answer this problem. So imagine I asked you the following thing. I took a per pixel distance between this image and this image. So for every pixel in this image, I would take the difference to the same pixel in this image, right? And you would basically get like values, and then you would take the norm, like the mean squared average of all of the pixel differences. Does that make sense? So basically, what that will give you is it will basically tell you the difference between the two images, and the only difference is that the ball has moved from here to here, right? Now I'm going to ask you a question. If I asked you for the derivative of this distance with respect to the position of the ball, what would be that derivative? So, like, what I'm asking you is, imagine that this image would be the pixel values in this image would be differentiable with respect to the position of this ball. So so there's a differentiable way. If you change this variable x, then the position of the ball changes. And now I ask you basically, if you formulated this loss and you did gradient descent on the position of the ball, what would happen? What you would like to happen, of course, is that this ball would move from there to there, right? You would basically backpropagate into x, and you would expect x to increase, right, until it matches the position of the ball in the other image, right? That's what you want to happen. But in reality, what will actually happen? Think about it for a moment. Yes?
Do you think the loss will be flat until they start overlapping?
Right. So, right, the loss is actually flat until they start overlapping. And there's another way of seeing this, which is if you take the position of the ball and you wiggle it, does the loss change? And the answer is no. The loss doesn't change at all. If you take the position of the ball and you wiggle it a little bit, nothing changes. It only changes once the ball overlaps with this other ball, right? Then the loss goes down, and then there would, okay. In other words, if you did this and you backpropagate it into the position of the ball, then nothing would happen. Everything would stay exactly as is, and the ball wouldn't move at all. And so it turns out in this framework that we have here, of like trying to get a depth estimate and at the same time trying to estimate the pose, you actually have a very similar problem. Let me explain the problem. Imagine that for frame t, you predict like a depth that is very wrong. So you're predicting a depth that maybe is like very large, or maybe you predict a depth that is very small, right? And now let's say for now the pose was fixed, and now you use that depth to generate the other image. Does that make sense? So I give you the pose, I predict a depth for this one image, and now you use the depth that you predicted to generate this other image from this other pose. What will happen? For instance, this image will be completely empty if the depth is very wrong, right? Because like the depth is really wrong, so you're trying to generate the image. It'll just, for instance, be an empty image. Or in other words, if the depth is very wrong, the pixels will just be at the completely wrong spot in the other image. Does that make intuitive sense? Or maybe I can visualize what I mean. Actually, yeah, this is probably easiest drawn, right? So like, imagine you had like one image here, and then you had another image here. Right? This image sees this area here, right? And now let's say we looked at this image and we predicted depth, and maybe it's a ball, and like we predicted the depth of a ball like to be like here. Of course, this ball will not even appear in this image, right? It'll just be an empty image. And then you run into exactly that problem. So now if you try to backpropagate into the depth for this ball, the gradient will just be 0. Because if you wriggle the depth of this ball, then it still doesn't appear in this image, and so the loss will just be 0. The gradient of the loss will just be 0, and you can backpropagate into this as much as you want, and nothing will happen, right? Or the same thing would happen even if the ball was in this image. Let's say you predicted the depth of the ball to be here, but in reality, if you looked at this image, the ball actually was here, right? So this is basically the position of the ball that you predicted, and this is the true position of the ball. The same thing will happen. Like if you now generate this image, you have exactly that situation over there. Like this ball is like here in the image on the left, and the true ball is here, so they don't overlap. So if you backpropagate into the position of this ball, it will never be correct. And so this is a problem that you run into whenever you have a situation like this with like depth prediction and pose estimation. And so does anyone know how we solve this kind of problem in computer vision usually? Can anyone think of a way how we might be able to solve that? So basically, let me tell you what you have to do intuitively. Intuitively, what you have to do is you have to find a way to make sure that that even if the ball is at a very wrong position, you still get a gradient that pushes the ball into the correct position. But does the problem make sense? Yes, Cairo? Noise, okay, this is a good idea. So maybe we can add noise to one image. So let's say we take this image and we add a little bit of noise. Unfortunately, no. Like that wouldn't change anything because like if you add noise to this image, then the noise is not a function of the position of this ball. So like you'll just get like a slightly different loss, but like you haven't actually done anything. Yes? Yes.
But like, I mean, if you have the same image, but like smaller scales, you might get some overlap, and that might.
That's right. So this is actually a very classical trick from computer vision, and the trick is basically what people call a multi-scale loss. You'll see it a lot in 3D computer vision, actually. So multi-scale, you can basically take two perspectives. You can think about multi-scale. Another way of thinking about is blur. So like imagine the following. I take this image here, and I blur it with a really big Gaussian blur kernel. Right? What would happen? What would happen is you would basically smear out this image, right? Like the position of this ball that was previously only here, like it would basically now be like a big smear. It would basically like be a big smear across a large part of the image, right? And now think about this loss. If you now think about this pixel-wise loss, if you wiggle the position of this ball, actually now, as long as this like huge blur, like smeared out blur kernel overlaps with the true position of the ball, you will actually get a gradient that tells you, oh, if I move this ball closer to the other ball, then the loss actually goes down, right? Does that make sense? Cool. And so another way of thinking about this is to basically do it like, downscale both images. So imagine what you do is you like do bilinear downscaling of these two images. So you take the image and you downscale it in like an anti-alias way, which downscaling is the same thing, right? You blur it and you downsample it. You blur it and you downsample it. And this is basically the idea of a multi-scale loss. So a very classical way of dealing with this is you take the two images and you just blur them, and then you compare them at several scales, and you just sum up the losses across all of the different scales. And then even if there is no overlap at one scale, there usually is an overlap at a lower resolution. And this is exactly also what this image does. So basically, when they predict their depth map, they actually predict depth maps at different resolutions, and then they actually they downsample the image also to these different resolutions, and they basically warp the image at these different resolutions, and then they sum up the contributions from all of these different resolutions across scales, and that's the total loss. So the total loss is basically the sum of losses across different scales. Does that make sense? So this is almost certainly something that you will have to deal with at some point in your life. This is something that is useful to remember. Actually, fun fact, like recently we wrote a paper called Diffusion with Forward Models, and we will actually talk about that paper in this lecture as well. And in that paper, I won't tell you where, but maybe when you read the paper or when we get to the paper, maybe you can tell me where. We forgot about using this exact thing, even though I talked about it in my lecture last year. I talked about it, I was like, yeah, obviously. And then we had something where this is actually very important, and we forgot about it, and we didn't use it. And actually, the result from the paper is very much worse for that reason. So maybe you can when you read that paper, maybe you can spot which experiment it is. Okay, so this actually was like this added like another, this is just a comparison to like previous methods, and in fact, this is the method we discussed earlier. So this was the paper from 2017 that we discussed. And as you can see, the improvement over that paper from 2017 with both of these tricks that we discussed, and there was actually another trick which was a principled way of not only dealing with disocclusions, but also dealing with moving objects, which we skipped, led to this like quite drastic improvement, right? So you get from here, this is the input image, which the depth that you predict is kind of can barely differentiate between all of these different objects. And now maybe you have an idea why, right? If you have thin objects like this lamp pole here on the top left corner, for these thin kinds of objects, these effects like disocclusions play a very big role. Because this object is very thin, when you move the camera, like you're disoccluding a large part of the background, and if you don't get it exactly, if you don't get the depth exactly right on the first try, then you're kind of screwed. So just the changes that we discussed in the loss and in this masking gave you this huge boost from this to a depth that looks like this. And this depth map obviously is much better. You can see, for instance, that the lamp pole is like very well and precise. You can see the tree in the background is like reasonably well captured. And like even this like very thin sign in the front is reasonably well captured, right? Cool. More results, whatever. And as we had discussed still before, there's still like lots of failure cases also in this part. So this is far from a solved problem. There's still every year papers at CVPR that like extend these things. But I would say that since this paper happened, nothing fundamentally changed. People have like made some small changes, but like fundamentally the same ideas that were proposed in this paper are still around today. So it's like not a drastic change. So you should be able to read any of these papers published now and kind of get an idea of how they work. Okay, so last little thing. So is this problem solved? No, it's not solved. The biggest problem with all of this, and we're going to talk about ways how we might solve that in future lectures, is that this really still only works for very simple camera trajectories. What I mean by that is all of these papers, as you can see, are done on these self-driving data sets, KITTI basically. And that has a good reason. It's because it doesn't work on any other data set. It only works on data sets where basically the camera moves into the scene and maybe the camera turns sometimes. But like for like scenes where you had a video of like maybe an object-centric data set where you move the camera around an object with like lots of rotation and translation, where you really have pretty unconstrained motion of the camera, none of these papers work. They just don't. And yeah, maybe you can think about why that might be. I'm going to give you a hint. The reason for that is, turns out, this part of the network. It's the part that basically takes two images and just predicts a pose. And it turns out, why is that? This part is actually really hard. We can think about for a moment like how hard it is to predict the relative pose between two camera images. And if you think about all of the things that are involved in that, right, you have to find correspondences, then you have to like figure out like triangulation, where are the correspondences, you have to reason about the pixel coordinates, you have to reason about all of these things. Turns out neural networks are really bad at that, if you just like do it in a black box way. So it turns out that there is better ways of doing this, but we'll get to that later. Okay, so this was a catch-up from the last lecture, which took half an hour, interestingly. So now we'll get to 3D representations, if no one has any questions. Any questions on this topic? Yes?
The reason that like camera pose from images or other sensors. So what's the benefit of using images?
Great question. So the question is like, I guess one, would it be fair to rephrase your question as like, why is it important to get the pose in a self-supervised way as well? Like, why not use ground truth poses is basically your question, right?
Right, like if you have like another sensor on the camera.
Yeah. So it is indeed the case that if you have a very well sensorized camera, then pose estimation gets much easier. And I would go as far as to say that maybe it's not a solved problem, but it like works really well. Like if you, for instance, on your iPhone, when you like boot up ARKit, your iPhone has a LiDAR, and then it has an IMU, and it has 3 cameras, and it has like all of these kinds of sensors. And if you do like sensor fusion with some deep learning in between, but it's like actually nothing fancy, it's basically just like sticking everything into a neural network and then like training it a little bit, then pose estimation works really well. And so you could say, well, actually, why not just use that? And the answer is that the motivation for all of this is to train it on all of the videos ever captured. And so what you really want to do is you want to use like internet scale data to train these things. You want to train it on millions of hours of video. And the problem status today is that even actually if you upload your video captured with your iPhone to YouTube, YouTube actually doesn't keep the IMU data. It throws it all away, as far as I know. So Apple probably has a pretty, well, actually Apple allegedly doesn't look at your data. So Apple probably also doesn't have a data set of like lots of videos with IMU data in it. So in fact, no one has a data set of like millions of hours of video that contain the that contain enough data to reliably draw out the camera pose. So that might change in the future, and then maybe this whole calculation will change. But my guess is that it won't change in the next 5 years. But maybe in the future, we will all capture videos and have all the metadata to back out the camera pose really well. But who knows? Not today. Any other questions? But this is actually a really good question because it touches on some it's a good question to keep in mind because like it's always a good idea to ask what is changing right now, like what is changing in technology, what is changing in hardware, and does that enable us to do things differently than we did them in the past, right? Fundamentally, actually, like GPUs were like the best example for that. Deep learning is basically a function of people looking at GPUs and be like, like no one's using these for training neural networks. I wonder if we can train neural networks with this. And ta-da, right? That was 2012. And I'm sure that will happen again. So this is a good question to keep in mind. Other questions on the depth estimation stuff? Cool. Okay, now we're going to talk. So far we talked about depth maps. Now we're going to go one step further and talk about actually actual 3D representations. What do I mean by that? Let me skip ahead a little bit. So the problem with depth is that, come on. Okay, so depth maps are a representation that represents the visible. They basically give you the geometry of every point that is visible in an image, right? So for instance, when I look at this chair and I would have a depth map that I would capture with a depth sensor, the depth map fundamentally only tells you about the depth of every visible pixel. But for instance, for any point that is occluded by this chair, I don't get any information about that point. Okay, so it doesn't capture the full 3D structure. If you were to like rotate the camera around, for instance, for this donut, you would see that the backside of this donut isn't captured at all. We don't know anything about the geometry of the donut. So the depth map fundamentally only tells you about the geometry of the visible part of the scene. So the same with all the models we just talked about. If there's a car in the scene, the model doesn't have any knowledge of the backside of the car. It only has knowledge about the part of the car that is visible. So we call these representations sometimes 2.5D representations because they are basically like they are 2D like an image, but then they also have knowledge about this like third dimension, but they only have like, they don't have complete knowledge about the third dimension. They only have like a half dimension additionally. So the question is basically, can we relax this image dependence constraint? Is there like, how would we represent occluded parts of the scene as well? And that brings us to surface representations. So the most straightforward way of thinking about this is going from depth maps to point clouds. Who knows what a point cloud is? Everybody, good. Okay, what's a point cloud? A point cloud is just a collection of points in 3D that live on the surface of, well, that's usually how we refer to, how we use point clouds in computer graphics anyway. They live on the surface of the 3D scene. So if you look at the scene, there would be points on any surface, including the surfaces that are occluded, right? So for the donut, you would also have points that live on the surface of the occluded side of the donut. Nowadays, right, like with LiDAR sensors driving around on cars, do note that a LiDAR sensor fundamentally also only captures a depth map when it drives around, right? Like it basically just gets the distance. But as you're driving through a scene, you oftentimes see an object from different angles as you drive past, right? And if you integrate all of these observations over time, in other words, you just put all of these depth maps into one, then you basically get a single 3D point cloud that includes information about parts that might not be visible from any given single scene by itself. So oftentimes these point clouds are still acquired by depth sensors, but then by integrating depth over time, we can basically get a full point cloud. So for instance, right, if you like move the camera around here, and the camera has a depth sensor. You can fuse all of these point clouds into a single 3D model. I think that you're doing that in homework number 1. Is that correct? Or is that homework number 2? Huh? Oh, neither. Okay. Did we remove that? Okay, we removed that part. So in the previous year, you would have to do that yourself, but not this year, apparently. That's good. Okay, some properties of point clouds. These are actually, we won't touch too much on these in our lecture, but these are actually extremely important for computer graphics applications and for real-world applications of all of these things. This is something important to keep in mind. Yes?
In that point cloud, how could you like see through the count?
Um,
Like, how do you know like the overlap?
I don't quite understand the question. How do you?
You can see points like below the cloud head.
Yeah.
Like how is that possible?
Right. So I think you're asking is like why don't the points occlude the back of the surf of the? And that's a good question. It's there's like a funny thing about point clouds, right? Which is the density of the point clouds. Like how many points do you put on the surface? Like how densely do you sample the surface? And in this example here, the surface happens to be not sampled very densely. And so, and then there's another little thing. So technically, each point is infinitesimally small, right? So technically, you have to make a decision on like when you render the point cloud, when you like render an image from the point cloud, you have to make a decision of like how big do you want each point to be in 3D, right? Because if you made it infinitesimally small, of course you wouldn't see it. It would just be nothing when you rendered it. So you have to make a decision, and in this case, someone made the decision each point will be 1 pixel wide. So in other words, the way this point cloud was rendered is you took the 3D points, you projected them onto the image plane, and then you just said every pixel that is hit by a point, we just make it blue. That's how this point cloud was rendered. But your question, of course, remains valid. If the points would be sampled so densely that for every neighboring point on the surface, you would always get a point, then you wouldn't be able to see the backside of the cow's head. You would just see blue. Does that make sense? Okay, so a few interesting things about point clouds. Point clouds are a little bit weird because they are unordered sets of points. So in other words, like on first order, if you just look about how this point cloud is saved on the disk, like how it's literally written in memory, it's just an unordered list of points. Why is that interesting? It's interesting because the point cloud as a data structure doesn't tell you anything about how close 2 points are to each other. Like it's just an unordered set of points. The set stays the same if you swap 2 points around. So in other words, like in the data structure itself, there's nothing that tells you this point here is closer to this point than this point is to this point. There's nothing in there that tells you about that. So in fact, you would have, if you cared about that information, you would have to compute it. You would have to compute the distance between points. And it turns out that this gives rise to real-world problems. Let me give you an example for a hard problem. If I give you a really big point cloud, and I ask you, give me the 10 nearest neighbors of this point, but the point cloud has 10 million elements in it, how would you do it? It's actually a really hard problem. Like naively, you would loop through the point cloud, right? And then you like would compare the distance to every point. It's really expensive. And it turns out there are whole papers written about this. Like how can you basically build data structures around point clouds that make it easy to query nearest neighbors in point clouds and stuff like that. So this is actually a practical concern. So point clouds are just sets, which means they're permutation invariant. So like by definition, if you shuffle the set around, nothing changes. They're unordered. So exactly as we said, like oftentimes they're just represented as an array of like points, like number of points times 3. And you need lots of, you need to build structure around point clouds to make them queryable for many real-world applications. And this is another really interesting thing. So we say that the points are sampled on the surface of the 3D seed, but there's a little bit of a bug here, which is the following. So this is actually related to your question that you just asked. So when you think consciously about like how you think about the surface, I already said it, right? You think about surfaces as surfaces, which means you think about the surface as like a connected thing. And you probably have an idea about the orientation of the surface, right? But point clouds don't have any connectivity information. So what that means is you don't actually know if 2 points like lie on the same surface. It could be, for instance, imagine that there's a sphere that would be floating in space right here, and you would sample the points on the sphere, right? And now the rest of the scene is also points floating in 3D space. There's nothing, if you sample 2 points, there's nothing that tells you whether these 2 points are connected, whether they lie on the same surface or not. And this is different from other kinds of 3D representations, which we're going to talk about another one in a moment. But this leads to lots of funny problems. For instance, it leads to a problem where you often don't know, is a point inside an object or outside of an object? Like if I give you this cow and I give you a 3D point, it turns out there's no simple computational way for you to answer the question, does this point lie on the inside of the cow or on the outside of the cow? It kind of is all the same. And again, you would need to build you would need to make some assumptions to answer this question. For instance, you would need to make the assumption 2 points are connected, or like they lie on the same surface if they're closer than like some threshold. But then maybe if you have sampled your point cloud via a depth sensor, for instance, you get lots of problems because actually points are sampled irregularly by a depth sensor. For instance, if you look at a surface at an acute angle, right, like then, and your depth sensor is sampling 1 depth value per pixel, and you look at a surface from an acute angle, then on the surface, the two, if I take a picture from here, then these 2 points might be neighboring pixels, but in real world, they're like really far away. So you have irregularly sampled the surface of the 3D scene, which makes it really hard to like use some heuristic based on distance, for instance, to reconstruct the surface afterwards, right? Does that make sense? So there's all kinds of weird problems that arise with point clouds. Okay, so and it turns out that these problems actually are very relevant for an application called computer graphics and video games. So for instance, let's say you want to put 3D objects in your video game. You really would rather have that when you render the 3D object, you can render surfaces. So which means that like if you look at a surface, you'd really rather have it that you really see, you really want to have like one green surface, for instance. You don't want like speckles of, obviously. Okay. So what is the representation that people use in computer graphics and in CGI? So when you watch a movie and there's like CGI in it, what is the representation for the 3D objects in the movie? It's always meshes. So what is a mesh? A mesh looks like this. You can kind of think about it as a set of like 2 different kinds of things. One is vertices and one is faces. And vertices are basically, you can think about vertices like as a point cloud floating in 3D space. So like the vertices are like a point cloud, but then meshes have one additional set of information, which is the connectivity between vertices. So so for instance here, right, you can see the vertices, and here you can see that each vertex is connected to neighboring vertices via an edge, and that is explicitly stored in the data structure, which vertices are connected to which. And in this case, this is called a triangular mesh, which means that the mesh is made up out of small triangles. So most of the vertices are connected to a number of neighboring vertices, and with each of them they form a triangle. And then these faces are the thing that defines the surface. So the surface of the mesh is now defined via these faces that are inscribed into like little triangles. And you can think about this as like a piecewise linear approximation of the underlying surface, right? So for instance, if you have a curved surface, what happens is that you'll have lots of little facets that approximate the surface of the 3D surface. Yeah. And of course, you can pick different resolutions, right? So for instance, here's a donut that is sampled at a really low resolution, which makes it very blocky. So it's a piecewise linear thing. And then as you increase the number of vertices and more faces, it gets closer and closer to like a round surface. And actually, if you watch like computer games from like 10 years ago, this is very apparent, right? Like lots of old computer games, like Lara Croft or something, like the face has like 6 vertices. And you can see every vertex, and you can see exactly what's happening, right? Nowadays, a single face of a person in a video game might have, like, if it's the main character, maybe 500,000 vertices. It's like completely insane. You have like, or like a car in like a game like, I don't know, say Cyberpunk, right? A car in a game like Cyberpunk might have 500,000 vertices. It's like basically a point cloud of like 500,000 floating points in space, and then this little edge information, right? And that's why, but like it is crazy to think that like, I mean, there's lots of other stuff going on in computer graphics, but it is crazy to think that fundamentally that's how we parameterize 3D objects in video games. It's just like millions of points and then like lots of tiny facets. And some video games, if you go really close up to an object, you can kind of tell. But then there's lots of tricks of how to actually like how to actually make it smooth. So there's like lots of interpolation tricks you can do to actually make smooth surfaces smooth. But I don't think we're going to talk about those. Okay, so a mesh is basically two lists now. You have one list which is the vertices, and then one list is the face. And the face basically tells you for each vertex how is it connected to neighboring vertices. Yeah, and now there's a funny thing, which is that like if you the way that faces are usually defined is like as a set, which tells you like the index of the vertex that is part of that face. So for instance, for the top row here, you have ijk, which is going to be 3 indices that go into this list and tell you the indices of the respective vertices. And then this list tells you these 3 vertices are connected to form a face. And now there's a funny thing going on though, which is that the order of these indices matters. So if you, for instance, take this is a quad, so we would call this this is obviously not a triangle, this is a quad, which means it's like a rectangle. If you store the you would pick some kind of convention. You would, for instance, say I'm always ordering my vertices maybe like against like counterclockwise. And now if you split the order of the vertices, you might end up with a connectivity like this. And this face obviously doesn't make any sense. So like the order of the vertex indices actually makes a difference in like the faces that you will generate for the mesh. Okay, we're going to skip this. This is not super important for us. Okay, and now something funny happens, which is that if you did a really good job at generating this mesh, then now you can answer the question if a point is inside the mesh or not. Because, and why is that? Because, like, think about it intuitively like this. Clearly, like, the surface has now you can compute a surface normal, right? Like, the surface normal is defined to stand, like, orthogonally on the surface. And a point is defined to be inside the shape if for every point that you, well, actually, this is not a good definition. Never mind, I got that wrong, actually. Forgot what I just said. This is actually not as easy as I hoped I could explain it. Basically, there is a way of making this decision easier, and the property that allows you to judge whether a point is inside a mesh or not is called whether the mesh is watertight. And like another way of putting that is, if the mesh has a hole, then the question remains very hard to answer. Like if you take this bunny and I give you a point that is in the bunny, imagine that the mesh was like super tight, it didn't have any holes, then you can imagine you can find an algorithm that checks whether the point is actually inside the bunny or not. But the moment there's a hole in the bunny, like one of these faces would be missing, and then the definition of inside or outside the bunny gets really weird again. So then it gets really hard to decide whether a point is inside the bunny or not inside the bunny. And this is something that computational geometry people write papers about. And it's actually an important thing for like things like physics simulation and stuff. It's actually an important question to answer. Yeah, we're not going to talk about that, but that's an interesting thing. So, and there's like, yeah, so now we're actually slowly getting into the realm of rendering. So this is interesting because if you think about the previous lecture, in the previous lecture, I kind of snuck in a notion of rendering. So let me define rendering for you. Rendering means is a process by which you go from a 3D representation to an image of a 3D representation. Like, basically, if you place the camera in the scene, what would the camera see? Rendering is an algorithm to answer that question, right? And if you think about the depth warping stuff that we discussed last time, that is in many ways one of the most primitive ways of doing rendering. Like I give you an image and you predict a depth for every point, and now you can say, okay, if I place the camera in the scene that looks at the same 3D scene from a different angle, this depth warping algorithm gives you a very easy way of answering this question. However, it had these limitations that we discussed last time, or like even this lecture, about like not being able, it only encodes information about the visible surfaces that are visible in one scene, like in one image. Any point that is not visible in the one image that is used to define the depth map, you will not be able to generate that. So now we get into a realm of actual rendering, which basically means I give you the definition of a 3D scene, which is, for instance, encoded as one of these meshes here. And because this mesh now really encodes the information about the whole 3D scene, from all the angles, now you can answer the question, if I place a camera anywhere around this cow, what does this camera see? The question that you have to answer, though, is what color does the camera see? So, of course, you could go ahead and you could just define this cow as being blue. Like every every face is just blue, and that would be totally reasonable. But you could also say maybe I'm going to give a color to every vertex. So like now, maybe each of the points has a color, and you could maybe come up with a way of like then coloring the face according to the color of the points or something like that. But actually for meshes, as you may know, people have thought about this, of course, a lot. Like how do you define the colors on the surface of the object? And this is something that is done via UV maps. So what that basically means is, if you think about the surface of this cow, the surface is actually a 2D construct, right? So the cow lives in 3D, but the surface is really a 2D thing. By which I mean is, what I mean by that is you could say, I'm going to define a mapping for every point on the surface of this cow. I'm going to identify it with a point in the 2D image. And this process is called UV unwrapping. So in this case, we took this cow and we mapped every point to a pixel coordinate in an image, and then we can just define the colors of the cow in this image. So for instance, here we defined the color of the cow, and then you can map it back onto the cow, and you can actually color the cow. This is called a UV map. And this is actually how it is done in video games. So in video games, you have these 3D meshes, and then there's an artist, and the artist does UV unwrapping, which means he actually literally gets, for more complicated meshes, it might be like lots of these images for each of the parts of the mesh. Like if you look at a car might have lots of pieces. It might have a tire. It might have the body of the car. It might have the window. And for each of these pieces, you might have one of these images. And like literally the artist will go in and like paint these UV maps, for instance, right? So, and edit these UV maps. Okay, so that concludes our discussion on meshes. We are not going to talk about meshes pretty much again. This is just something to keep, yes?
Oh, sorry, just ask, are the UV maps always square, or are they like?
And they are always square, but sometimes they have empty regions. So, yeah. Other questions? Okay, so actually, did you guys learn about meshes before? Who had learned about meshes before? Okay, not everyone, good. So meshes are like a funny little thing because meshes were invented to solve a computer graphics problem, which computer graphics tells you the question, answers the question of you go from a 3D scene to images of the 3D scene. Like how do you simulate that process? But in computer vision, we are interested in inverse graphics. So we're interested in going from images to 3D scenes, right? But because meshes were designed for that forward process and not for the inverse process, actually they are not very useful for the inverse process. And this is kind of, this was something we kind of had to learn the hard way over the past, this is something we learned over the past few years, I would say over the past 8 years, that initially people thought like, oh, wait, we have all of these, like, if you look at Cyberpunk, for instance, or in any modern video game, it's actually very impressive. Clearly this video game can render out these scenes photorealistically. So then you might think, oh, because this thing can do such a good job at rendering photorealistic scenes, it must therefore be useful at like doing reconstruction as well. Like why can't we use the same kind of tool set we have built for generating images to go from images back to 3D scenes? And we had to basically learn the hard way that meshes are not a very useful representation for that purpose. So actually meshes have very little applications in inverse graphics. And we're going to, and I hope at the end of this class you will have a better idea for why that is. But this actually concludes the discussion of surface representations. We talked about meshes and we talked about point clouds. Now we're going to talk about volumetric representations. Screw this, yeah, whatever. Okay, so surface representations are representations that only tell you what is on the surface of things, unsurprisingly. Volumetric representations tell you also something about the 3D neighborhoods of things. So not like surface representations only basically tell you something about like surfaces embedded in 3D. And the point of a volumetric representation is to also tell you something about all the rest of space, right? Okay, and now we're getting into a territory that was a hot topic of research over the last 3 years. Okay. Let's call volumetric representations field parameterizations. Let me tell you why that is a reasonable thing. there's this definition for field in physics, and a field is a physical quantity represented by a scalar, vector, or tensor that has a value for each point in space and time. So for instance, forget about time for a moment, although that might become important later. Think about space. This is a room we're in, right? You could say this room can be parameterized by a field that maps every 3D coordinate. It's like a function that maps every 3D coordinate in this room to the properties of the room at that 3D coordinate. So for instance here, I don't know, there's like properties that tell you that this is air, and then here there's properties that tell you this is like wood or something like that, right? And the property of volumetric representations is that it tells you that there is like a way of creating this representation for every point in 3D space, which is different from a mesh. A mesh only tells you something about points that are like included, like that are on the surface of the mesh, right? Okay, so the first question to answer is if you pick such a volumetric representation of space, like a representation that densely maps every 3D coordinate in space to the properties of that 3D coordinate, how do we actually represent the notion of a surface, right? Is it clear why that is why that is not obvious? Like how, if you have a function that maps like every 3D coordinate to what is at that 3D coordinate, how do you have a proper definition of what constitutes a continuous surface? And here's a few different ways of doing this. One is the so-called occupancy field. So the occupancy field is basically a function that for every 3D coordinate tells you whether that 3D coordinate is occupied or not. So for every 3D coordinate, maybe here, this is all free space, you would say this is unoccupied space, this is just air, so there's nothing here. So the occupancy field would evaluate to 0, so any coordinate that is here will evaluate to 0. And now the moment you get into a surface, you say, well, here now the occupancy is 1, this is occupied by something, right? Okay, and now it is possible to define the surface as the level set of this occupancy function. Does everyone know what a level set is? Who doesn't know what a level set is? Okay, yep, it's fine, yeah. Level sets are, the level set of a function is the set of all points where that function evaluates to a certain value. So for instance, if you have like a, so for instance here for this occupancy function, the level set, this is actually the best example I can come up with. So for this occupancy function, right, like we said, here there's like, for instance, this little square. So you have inside the square, and this gray space is free space, so there's nothing here. So outside of the square, the occupancy function evaluates to 0. Inside the square, the occupancy function evaluates to 1. And now on the surface, the occupancy function will at some point go through 0.5, right, if it's continuous. Like, let's assume it's continuous forward. Then the level set is all of the points where the function evaluates to 0.5. So in this case, it will be exactly the surface of the square. So you can basically, in other words, define the surface via the level sets of this continuous function that you defined in free space. For instance, if you pick the occupancy function, if you pick 1 to be inside and 0 outside, then 0.5 might be a reasonable definition of what is a surface. And then if you pick that definition, then afterwards you can, well, we'll talk about that later. Then you can generate an occupancy function for, actually, you can imagine that if I give you a 3D object now, with this definition, you would be able to build a function that evaluates the occupancy of that object, right? Okay, here's another function which is often used. It's called the sign distance function or the sign distance field. As the name suggests, it's a distance field, which means for every point in space, it gives you some distance. And what distance does it give you? It gives you the distance to the closest surface in the 3D scene. So, for instance, for this point, other than myself, the closest surface might be a point here on the chair. So the sign distance field, when you create at this 3D coordinate, will give you the distance to this 3D point, which, like, let's say is like 50 centimeters, right? And what is the surface? Well, the surface is going to be the 0 level set of the sign distance function, right? The set of all points where the sign distance function evaluates to 0 is going to be the surfaces of the scene, by definition, because the distance of all points that lie on the surface is 0. And oftentimes there's a convention which says the sign distance field has a convention usually of being positive outside the shape and negative inside the shape. So if you pick a point that is outside, it'll give you the distance as a positive number. If you're inside an object, it will give you the distance to the closest inside of the object as a negative number. Yes?
Talked about like it being hard to figure out whether something is inside or outside of an object.
Yeah.
So how do you come up
Yeah, this is a very good question. So first of all, let's ascertain one thing. Like, if I gave you a signed distance function, the query that we discussed earlier, whether something is inside or outside of an object, gets really easy, right? I give you the signed distance function, I give you a point, you query the signed distance function. If it's negative, it's inside. If it's positive, it's outside. And actually, that's kind of useful. For instance, in video games, this is often used, these signed distance functions are often used in physics simulators to evaluate if two things are colliding. You basically take 3D two objects, you figure out their signed distance field, and then when they're intersecting, like how do you detect whether two things are intersecting? You basically take the points that are on the surface of one shape, and for those points you evaluate the signed distance function of the other object, and then you check if any of them is negative. And if any of them is negative, then they intersect, and then you can call your algorithm that deals with collisions. So this is a common way of dealing with collisions. But now your question is like, let's say you want to fit a signed distance function, is I guess what you're asking. Well, we're going to talk about that later. Good question. Keep it in mind. But actually, the answer, no, we can talk about it now. The answer is very boring. The answer is that in practice, the first paper that was written recently in 2018, on like using these signed distance functions in like inverse graphics, just took a data set of meshes, and then it pre-processed all the meshes to make them watertight, which basically means they have no holes. And then they called an algorithm that manually computed the signed distance, and then they used that for training their neural networks. So that's the real answer. So the answer is it was kind of lame. Okay, so yeah, actually I just, one property that is good to keep in mind, because it'll come up again later in rendering, is that the signed distance field has a funny property. If you ask for the signed distance value of any point in space, the signed distance value is equivalently the radius of the biggest sphere that you can draw around that point that just barely touches the surface. So for instance, for this point, the biggest sphere you can draw will barely touch the surface of this thing, and it turns out the signed distance value is exactly the radius of that sphere, right? Which kind of makes sense. So you can again think how this might be very useful in a number of like computer graphics applications. For instance, when you want to detect collisions, right? This is very useful for anticipating if a collision would happen, right? Because if I give you a signed distance function and I give you a point, and you evaluate the signed distance function, it might tell you, oh, you're like really close to a surface. Versus if I just give you a mesh, right? Imagine how you would be able to make that judgment call. Again, you would basically, or like a point cloud, you would have to take that point and you would have to compare it to all the points in the point cloud to figure out if you're close to the surface or not, right? So having the signed distance function kind of amortizes that computation. It allows you to make that computation much faster. Yes?
Is there a notion of frictionality?
Directionality.
Right, because you're like there's one point on the sphere that's touching a square.
Yeah.
So what if there's like multiple surfaces along, like a distance r away from the?
Oh, you mean what if like there's several points? Yeah. So this is a good question. So that gets into like more geometry territory, but like it turns out that there is something called a medial, actually, what when you ask the question, what happens? What do you mean with what happens? What happens with the value of the signed distance function, or?
Right, like I guess in practice, does it actually matter if there's multiple points?
No,
Okay.
it doesn't change the definition. But something does happen, which relates to the gradient of the signed distance function. So let's think for a moment. If you think about the gradient of the signed distance function, for all the points that are close to, like, for any point here, if you take the gradient of the signed distance function, well, first question, the derivative of the signed distance function with respect to its input. Whoop, almost died. Okay. So if you take a signed distance function, this is kind of, okay, this is SGF of x. What does it do? It maps R3 to R, right? It maps a 3D point to R, okay? What is the dimensionality of D? Well, actually, this is, what is the dimensionality of the gradient of x with respect, of the signed distance function with respect to its input? 3. it's a three-dimensional vector, right? So it's a three-dimensional vector. Okay. And why is that, right? The gradient, okay, and which direction, if I give you any function, which direction does the gradient point into? Calculus. Does it point in the descending direction? Like if I give you this function, yeah, sorry, like I guess it's always hard to like, so I guess, oh, this is actually not a function at all. So let's try that again. So let's say I give you this function here, right? This is like some function, this is x, this is f of x, and now I give you this point here, right? So the gradient of this function is has how many dimensions? Just one, because it's x, it's a scalar function. So d dx is 1. Okay, so if you take this point, which direction does the gradient point into? Right, it points in the direction of the steepest ascent of the function, right? So the gradient always points in the steepest ascent of the function. Okay, so for the sign distance function, what is the direction of the steepest ascent in any direction? That's right. It's the normal of the surface. If you're on the surface, right? Like if you're close to the surface, then clearly the way you, well, sorry, it points away from the surface. Yes, it always points away from the surface, right? Because the direction of the steepest ascent is you go away from the surface, orthogonal to the surface, right? And on the surface, it turns out the gradient of the sign distance function is exactly the surface normal. Like the normalized is there, so you have to normalize it, but it's exactly the surface normal. Okay. And now that kind of answers, so the gradient of the sign distance function is sensitive to objects that are, to that property that you just discussed. Imagine, for instance, that like there's one object that is ever so slightly closer to this point than this thing. Then if you think of like, okay, I hope I can draw, I'm really bad at drawing, but like I'm going to give it a try. Let's say you have two objects here, and I pick a point that is ever so slightly closer to this surface here than it is closer to this surface here. If you move that point to the center line between the two surfaces, what happens? The gradient switches the sign, right? It like suddenly it goes from like pointing to one surface to pointing to the other surface. And so in other words, the gradient is discontinuous at those points. So the gradient of the sign distance function is sensitive to the placement to these things, but the sign distance function itself is not. Cool. Or in other words, when I say sensitive specifically, the sign distance function is continuous, but the gradient of the sign distance function is discontinuous at that point. And there's lots of interesting properties, but we're actually not going to talk about them now. Otherwise, we're going to be sitting here tomorrow. Implicit surfaces. Great, exactly. So this is what the sign distance function looks like for a number of, so these are the level sets of sign distance functions. So here's a car. This is a visualization of the sign distance function. And you can tell here, what you see here, these shells are the level sets of the sign distance function, which is like you pick a value for the sign distance function, and then you visualize all the points that have that value. So it's all the points that have a constant distance to the surface of the object. Looks pretty cool. Right, actually, this is exactly the question that we answered before. So, like, if you have the occupancy function or the sign distance function, it's very easy to answer if a point is inside or outside the shape. But, kind of almost as the dual of that, now it gets really hard to answer questions about surfaces again. So, in fact, if I give you the sign distance function, how do you find the surface? You first have to find the set of all the points where the sign distance function evaluates to 0. But how do you do that? Like, we actually just discussed it. Like, one way is you start with a point, and then you do gradient descent, right? So, like, you take the derivative of the sign distance function, and then you walk in the direction of the steepest descent. So that is one way how you can find the surface. But if you do that, like, let's say, for instance, we have some kind of object. You have some kind of object, I know. Don't judge. So you have some kind of object, and now you want to find the surface. What could you do? Well, you could say, oh, I'm going to place a lot of points around, maybe around the object, and then I'm going to do gradient descent for all the points, which eventually I will find the surface. But then what ends up happening is that the points will not regularly sample the surface. Like, the points will invariably end up crowding on some parts of the surface, while other parts of the surface will not be sampled well. So, for instance, it's really hard to make a point that ends up on the on this little corner, and that's exactly, of course, for the reason that the gradient exactly switches the direction on this little axis here, right? On this little axis, the gradient switches direction, so if you just do gradient descent, you know. Okay. So basically, if I give you a sign distance function or an occupancy function, it gets really hard to reason about the surface, versus if I give you a mesh, then it's much easier to reason about the surface. And it turns out, so because that is so, and because of computer graphics, which exclusively deals with meshes, or like, it's not true, but like which largely deals with meshes, there is a number of algorithms to extracting the mesh. If I give you a sign distance function, or if I give you an occupancy field, how do you actually get the mesh out of it? And one of these algorithms is called marching cubes. And it's a really brilliant algorithm. There's actually, just at SIGGRAPH 2023, there's a paper from NVIDIA, which is called FlexiCubes, which is the most recent differentiable version of like an algorithm like this. So again, this is a very up-to-date research topic. But the marching cubes algorithm is really old. Do I have to? Oh, I don't have the citation here. Sorry. Anyways, the marching cubes algorithm is really old. The idea of the marching cubes algorithm is very simple. You take the sign distance field, or like the occupancy field, and you just evaluate it on a regular grid. So you just define a regular grid, you evaluate the sign distance field at every point. And now it turns out you can enumerate a number of different cases. So if you look at this 2D thing here, right, what does it mean to extract a mesh? You basically want to decide when do I want to generate a vertex where do I want to place my vertices, and where do I want to place my faces? And the marching cubes algorithm just enumerates all possible cases of a surface lying in a voxel, in like a cube, right? A cube has basically 12 edges, right? A cube, I had to think of there for a moment. A cube has 12 edges, right? And basically, if you think of all of the different ways a surface can lie in a cube, it will always uniquely intersect some subset of these edges. So for instance, if there's no surface in the cube, then the surface will not intersect any of the edges, right? In other words, what does that mean? How can you test that? You can evaluate the 8 corners of the cube. You can evaluate the sign distance function at these 8 corners, and you can ask, does the sign distance function switches sign between any of those two? So for instance, if the sign distance function switches the sign between this corner and this corner, then it means that the surface intersects the edge. Right? So if the sign distance function changes its sign from here to here, so this one is negative and this one is positive, then it means that an edge must lie and intersect that edge, correct? And it turns out that you can just enumerate all of the possible cases where the sign distance function switches sign for the different edges of the cube, and then you can just say, okay, for these different cases, we're just going to place the vertices of the mesh at the corresponding locations on the edges or corners of the cube. And then you can basically go from a sign distance function back to a mesh, and you can extract the surface. But you can already tell that if there's like something very high frequency, then you're going to miss it. So if you want this to be accurate, then you have to sample the sign distance function really densely, and that's very expensive, and then all kinds of problems arise. But this is the high-level idea. Okay, any questions to this part, which was sign distance function, occupancy function? So basically, volumetric ways of defining 3D geometry. No? Okay. Any other feedback, hopes, dreams, fears? We're good. Okay, so now we're going to answer. Now we're going to drift off into deep learning land a little bit, because we're going to next answer the question: how do we actually parameterize this 3D function? So, okay, this is fine. We now have defined our 3D function in space. For instance, the sign distance function. We have a function that maps every 3D coordinate to some value, sign distance value. But how in a computer do we actually parameterize this function? And this was basically something that I worried a lot about in my PhD. So this was what a large part of my PhD was about. So there's a number of different choices. There's, and it turns out actually, looking back, this is, well, we have learned a few things since then actually. But like on a first order approximation, you can say, oh, we're going to have discrete parameterization. discrete parameterizations, then we can have like continuous parameterizations, and we have hybrid parameterizations. This is actually not a good way of putting this. What I should actually say is you have explicit parameterizations. Difficult terminology. You'll see in a moment what I mean. Okay, so let's first talk about voxel grids. So one straightforward way of parameterizing 3D functions is as a voxel grid, right? Which means you just, okay, what does that mean? A voxel grid just takes the domain of your function, and then you just discretize it into like little boxes, little squares, right? A pixel, for instance, is a 2D voxel grid, which is a function that is just discretized on the pixel grid. And for every little voxel, you'll just store a value. So for a signed distance function, of course, right, you can take your signed distance function, you have a voxel grid, and then you store the signed distance value in every voxel. Ta-da. Easy. And as you might know, actually we discussed this last time already, you mentioned that everyone in this room understands bilinear interpolation. So how do you query the voxel grid at values that don't fall exactly on the corner of a voxel grid? Well, you have to do interpolation. So if I take so the voxel grid, let's say for instance here, the voxel grid might store values at the corners. So you have F1, F2, F3, F4. So these are like some values, for instance, in an image, these might be colors. But now you want to get the color of like a pixel that doesn't lie exactly on the grid. What do? You do interpolation. So like bilinear interpolation or trilinear interpolation. And that's why when I just said like discrete parameterizations versus continuous parameterizations, that is actually a little bit weird, right? Because it's very easy to take the voxel grid, which on first sight is discrete, and then just define something on top that allows you to sample it at continuous 3D locations via interpolation. Okay, and now the thing is that are you guys familiar with like a notation like this for interpolation? So if you want to, so here we have our function. Let's imagine this was the signed distance function. And the signed distance function is, you want to query it at a continuous location, like here. And at this continuous location, you want to compute the value. And for that, you have to interpolate the values that lie on the four corners of the grid. And the values that lie on the four corners of the grid might be written like this. So you have like, k is like a distance function. So you take the x coordinate where you want to query it, and xi are the locations of the four corners. And k gives you, for instance, the distance. And then the value at this continuous location is basically a interpolation according to this kernel function of the four values that are on the corners. Have you seen this formulation before as like interpolation kernels? You're nodding? Yes, no? Or does this, yes, no? Okay, so this is actually, this is like something that's useful to understand in computer science in general. So we're gonna go through it in a little bit more detail. You know bilinear interpolation, right? Like, what is the formulation of bilinear interpolation that people have explained to you like some time ago? Sorry, I'm putting you on the spot, but it's fine if you.
It's been a while. So.
Yeah, but basically the idea is, right? You have a 2D coordinate, and then you have like values on the grid around it, and then you basically want to do some weighted sum, right? Some weighted sum of these four values, right? And now the question is, how do you get the weights? Exactly. You do the distance, and then you normalize the distances, right? Okay, good. And so now perfect. So now this idea of like normalized distances is captured in this kernel function k. So this k here is basically the function that tells you if I give you a continuous coordinate in the grid, and I give you the coordinate of the closest of a close point that lies on the grid, then what does this normalized weight evaluate to? So, for instance, here the k of x and this index 2 would probably be the largest value, right? And then the k for the other ones might be lower, and they will all sum up to 1, right? Okay. So this is the notion of this interpolation kernel. So this thing here we would call an interpolation kernel. Does that make sense? Okay, good. Okay, keep that in mind, interpolation kernel. Okay, so voxel grids. Who has worked with a voxel grid before? Okay, but all of you have worked with pixel grids before, I guess, right? Okay, so one problem with voxel grids is that if you want to use them to parameterize 3D functions, they blow up in memory really quick. So for instance, if you want to parameterize this room, which is you want to parameterize this room with the amount of detail that would allow you to differentiate like the texture on this like chair. The voxels would have to be like maybe this large, right? Okay, so how many voxels is that? It's like probably, okay, I have no idea, but it's a lot. It's like a lot of voxels, right? So the side length, the resolution of this voxel grid would be humongous, and the problem is that the number of voxels goes cubically with the side length, right? So you'd be looking at like a bunch of voxels, like a billion, right? Like easily. If the side length is 1,000, then it's like 1,000 times 1,000, a million, 1,000 times 1,000, a billion. So this grows really quickly. So that's a downside. There's upsides, which is that if I give you a function as a voxel grid, it's really fast to evaluate it at any 3D coordinate. And why is that? It's really fast because it's very, like, imagine you store this voxel grid as an array. It's very easy to make the indices of the array basically keep track of of where you are in the voxel grid, such that when I give you a coordinate, you know exactly where to look in the array, and then you can immediately retrieve the value without any additional shenanigans. So voxel grids are really, really fast to evaluate. They are also actually, from a deep learning perspective, very convenient to process, and that's because they expose locality. What does that mean? When you look at convolutional neural networks work really well because they make use of the fact that locality matters in images. Like things that are close together, they usually have something to do with each other. In a grid, it's very easy to like look at the value of a pixel and then find the neighboring pixel and then compute a function of these two neighboring pixels. Compare that to the point cloud that we discussed before. In the point cloud, just finding the 10 nearest neighbors is a computation all by itself. So if you want to define a neural network that like a convolution on point clouds that looks at neighboring values of the point cloud, it's really complicated because you first even have to figure out what are the neighboring points for each point. So in voxel grids, it's very easy to figure out locality. But unfortunately, it's like basically intractable in higher dimensions. So in 3D, you know it's fine, like a billion values in 3D, whatever. But now if you have the time dimension in addition, right, then you have 4D. Now side length of 1,040, a trillion values. Like, and it starts to get like rather complicated. Okay, and now I think I should let you go because it's already 4 p.m. So I'm going to do that. And we're going to talk about multi-resolution representations next time. Cool. Thanks, everyone.